All right, so today we're going to be doing algebraic manipulation. We're going to do fractions and squeeze theorem. So squeeze theorem has to do with the trig. Fractions obviously are going to look like these first couple examples where you have like fractions and fractions. So the big key thing today is to remember how to keep, change, flip. All right, that's what goes in those first couple blanks. Keep, change, flip. You are not going to cancel anything out until you've done the keep, change, flip. All right, that's normally where people mess up, is they start canceling too soon. So on example 62, we need to get a common denominator to the top so we can actually subtract the fraction 1 over x minus 5 and the minus 1. Does that make sense? So we're not going to mess with the bottom. We're just going to try to get that guy to be a common one big fraction. So we're going to make the denominator over 1, and we're going to multiply the top and the bottom by x minus 5. Because whatever you do to the bottom, you have to do to the top. All right, so I'm going to rewrite my problem now. Once you figure out what your common denominators are, rewrite it. The x minus 6 is going to stay x minus 6. So we're not going to mess with the x minus 6 at all. The top fraction we're going to write as one giant fraction. So we don't actually want to keep it as two separate fractions anymore. We want to make it one big fraction. And when you are making, like when you subtract the fractions together and you make it one fraction, the common denominator stays common. So the x minus 5 is going to stay x minus 5 on the bottom. Does that make sense? Okay. And then on the top, we're going to just put all of the top stuff on the top. So like the 1 minus x minus 5, we're going to write all of that on the top. Make sure you're using parentheses, 1 minus, and then x minus 5 is in parentheses, because that negative is going to get distributed to both the x and the minus 5. All right, so I'm not canceling anything. This is where people get confused, is because they try to cancel out the x minus 5s right here. Do not do that. All right, right now all I'm doing is I'm going to simplify the top, and I'm going to rewrite that again. The limit as x approaches 6, 1 minus x plus 5 over x minus 5 over x minus 6.
Do we even have to do this step before?
No, I mean, you can skip. Yeah, you can skip steps. I just didn't want to skip steps on the first example. But yeah, so you can skip some steps if you can do that in your head. All right, so after we simplify the top there, we are going to do our keep, change, flip. So the top fraction we're going to keep, we're going to change the sign to a multiplication, and we are going to flip the bottom fraction. The bottom fraction is technically over 1. So if you like to put the little over 1, you can write the over 1. And then I'm going to rewrite it all again. So the limit as x approaches 6. We're going to keep the top, and I'm going to add up the 1 and the 5. So negative x plus 6 over x minus 5 times, and then 1 over x minus 6. All right, so we kept the top. I did simplify. I added the 1 and the 5. Change sign to multiplication and flip the bottom. Once you keep, change, flip, a lot of times, this is where you can cancel. Now on this one, the x minus 6 and the negative x plus 6, I am going to be able to cancel those, but what do you have to take out? A negative. So you can take out a negative to make that an x minus 6, and then you can cancel the x minus 6. So now I have the limit as x approaches 6. Hold on, I'm going to do it here in a second. I can't remember what I was saying right here. Yes, that's what I was saying. Okay. So we're going to, this is where it's, yep. Wait for it. Haha. Here we go. Okay, so took the negative out, x minus 6. X minus 6 is canceled. And I'm going to rewrite it. You still have to write limit because we have not directly substituted in. On top, I'm left with just a negative 1. And on bottom, I'm left with an x minus 5. So after you've canceled, now's where I can directly sub in that 6 in the, into the x spot. So I get -1 over 6 minus 5, which is just -1. Okay? All right, so we're going to do the next one. So first step is we got to get a common denominator. So what am I going to multiply the right fraction by? X plus 4. And what are you going to multiply the left fraction by? 4. And times 4 and times 4. So once you get your common denominator figured out, we are going to rewrite this limit. And we're going to put the top fraction as one giant fraction with the common denominator as 4 plus x plus 4. The top part, the 4 minus x plus 4, we write that all on top. So 4 minus, and then in parentheses, x plus 4, which if you can do that step in your head and skip that step, that's fine. All right, after you write the two fractions together on top, we are going to keep, change, flip. So we are going to keep the top fraction, change the sign to a multiply, flip the bottom around. If you want to put it over 1, you can. So you can kind of see the fraction getting flipped. All right, I'm going to distribute out the negative also in this step to just save me a step. So 4 minus x minus 4 over 4x plus 4 times, and then flip it over 1 over x. So after your keep, change, flip step is when you can start canceling stuff. So what cancels? The before the x's cancel though, the 4s, and then the x's. What is still on top? A -1. Yep. So we have the limit as x approaching 0. The -1 is still on top. The 4x plus 4 is on bottom. And so now I can directly sub in the 0. And I got 4 times 4, which is going to give me -1 over 16. Okay, one more fraction problem and then we're going to be done. Hopefully you're going to start seeing the pattern that happens with these guys, because like I said, they're not tricky problems. It's the same type problem over and over and over again. So on this one, I am going to multiply the second fraction by what?
The bottom of the first.
Yep, 2 plus x on top and bottom, and the first fraction is going to be times 2. All right, and then I'm going to write it as one giant fraction. So the limit as x approaches 0, x is on the bottom. And then for the top fraction, the denominator is 2 times 2 plus x, or x plus 2, it doesn't matter. And then all of this stuff on top is going to just be on top. 2 minus, and then in parentheses, 2 plus x. So once you get it all as one fraction, we are ready to keep, change, flip. Keep, change, and flip. And when I keep, change, flip, I'm going to distribute the negative. So the limit as x approaches 0 of 2 minus x over 2 plus x times 1 over x. Wait for it. It's coming. So 2 minus x over that we're going to leave the same. And then the x over 1 we're going to flip to be 1 over x. Okay, so then here, what cancels? The 2's and then the x's. What is left on top? -1, and on bottom I still have the 2 plus x. So notice I'm still writing the limit. I still have to write the limit until I directly substitute. And so I'm going to directly substitute in 0 for the x. And I get negative 1 over 4. That was an ugly 4. Okay, fractions. We okay with the fractions? Now for squeeze theorem. All right, so squeeze theorem is going to say that I have this fraction g of x that is smaller than everything else. All right, so g of x here, that is smaller than everything else. And I've got this fraction, or not fraction, function, I'm sorry. Function h of x, that's bigger than everything else. And then there's this function f that's in between them. And so what squeeze theorem is telling me is that if the limit of the small function, the limit of the small function and the limit of the bigger function both equal the same thing, it will squeeze the middle function, and the middle function will also be the same limit. It's kind of obvious. It's like, okay, well, if the top one, the one that's bigger than everything, its limit is L, and the one that's smaller than everything's limit is L, that means that the middle function's limit has to be L.
So it's just a compression.
Yes, it just like squeezes them together, and so the middle one gets squeezed with the other ones, and the limit will also be L. Okay? All right, so why is this important? Well, it's important because the squeeze theorem helps us prove these following limits. So the limit as x approaches 0 of sine x over x is 1. And the limit as x approaches 0 of 1 minus cosine x over x is 0. So these limits right there in that little box, they're something that you just memorize. The squeeze limit proves them, but we're not going to do that whole proof because it's kind of long and it doesn't really matter. It does not matter if the sign is on top or bottom, so I did put both of them on there. It could be sine x over x, or it could be x over sine x. And then for the cosine, it doesn't matter if it's 1 minus cosine or cosine minus 1. All right, so both of those work. Now, the way that I memorize these guys is it's always x approaching 0, no matter what. And then the sign has an I in it, which kind of looks like a 1. Whereas the cosine has an O in it, which kind of looks like a 0. You gonna see? Okay, so that's how my brain's got it figured out. And then everything else, I just remember the cosine needs 1 minus or minus 1. So the goal for squeeze theorem is to manipulate these trig functions so I get sine x over x, or 1 minus cosine over x, to solve them out. All right, so back from pre-cal, what's a way that I can rewrite tangent? Good, sine over cosine. So I'm going to rewrite this guy, the limit as x approaches 0. Sine x over cosine, and then it's still all over x. Now, because I have fractions and fractions, I'm going to keep, change, flip. So the limit as x approaches 0, I'm going to keep the sine x over cosine x, change the sign to a multiplication, and flip the x over 1 to be 1 over x. All right, is that okay so far? Okay, so now if you look here, I see I have sine x over x, which is what my special trig limit is. Right, that was the one of them. So, and because this is all multiplying, I'm just going to rewrite this so the sine x and the x are on top of each other and the cosine is over on the other fraction. Because multiplying, it doesn't matter the order that you multiply in. 2 times 3 is still 3 times 2. So I'm going to rewrite this, the limit as x approaches 0 of sine x over x times, and then 1 over cosine x. I'm just going to kind of flip those guys around, and I can do that because multiplying. You can't do that if you're adding and subtracting. All right, so now I know from the special trig limits that the limit as x approaches 0 of sine x over x is 1. And I can directly substitute in 0 into this other part. So it's cosine of 0, which what is cosine of 0? 1, and 1 times 1, which would be 1. So my limit is 1. Does that kind of make sense? A little bit, maybe?
So it's just like the trig identity. So like,
Kind of, yeah. You like your, but my goal for this is to get it to look like one of these guys. So it's like trig identities, but you can't see that. I want to get it to look like one of these guys. Mm-hmm. All right, so on this one, I have the limit as x approaches 0 of sine 4x. So the 4x is inside the trig. You cannot pull that 4 out. The 4, it's like inside that trig. So what I'm going to do instead is I want to turn this guy in, the bottom guy, into a 4x. So it kind of follows the same pattern.
so it'd be 4.
Mm-hmm.
Okay.
Now, if you multiply the bottom by 4, what else do you have to do? Multiply the top, so you're not actually changing the problem at all. And if you multiply the top by 4, that's just a constant. You can just pull that coefficient out and do 4, the limit as x approaches 0 of sine 4x over 4x. Right, so this 4 here that's in the very front, that's the one that I just multiplied to keep everything even. And then I know that the limit as x approaches 0 of sine 4x over 4x is going to be 1 times by this 4. So your final answer is going to be 4. Is that kind of okay?
So the constants in front of the, like in front of the x and sine and below it on x, they just.
You can pull those out.
You pull all 3 of them out?
No. You only can pull out the
The one in front of sine?
the one in front of sine. This one has to stay, so it matches with this sign. This is the only one that you can pull out. But this guy here, the limit as x approaches 0 of sine 4x over 4x is your special trig limit.
And the special trig limit doesn't assume 1 in front of the x and assume 1 and
Yes.
the sine x. So if they're the same,
As long as they're the same, that special trig limit
it
works.
just cancels to 1 always.
Yes.
Okay.
Yes.
Oh, okay. Wait, so is it on the right where it says sine 4x over 4x, do the 4s
These 4s?
cancel?
This whole limit turns to 1.
Oh, because it gets like 1 over 1.
Yeah.
And-
Yeah.
Oh.
So this whole thing is the special trig limit that turns to 1.
The answer is 4, right?
Yes, so the answer is 4. Okay, so let's try the other one, and I can work out some other ones on the board over there from your homework if we want to do them together after I'm done here with the notes. Okay, so on this next one, I have the limit as x approaches 0 of sine x squared over x. So I'm going to split up my sine x squared and write it as sine x times sine x over x. And that way I can pull out this special trig limit, the sine x over x. That's going to be 1, and I directly substitute 0 into this remaining one. So the sine x over x turns to 1. 0 goes into sine, so sine of 0. Does that make sense? And what is sine of 0? 0. So 1 times 0, which is 0. It's a little tricky. Now remember, we also have L'Hopital's rule that we will fall back on when we learn that. So it is not the most horrible thing if you don't get the squeeze theorem. Mm-hmm. Yeah. Yes. So L'Hopital's will help us once we do that. So it is not really the worst thing ever if you don't get it. You might see it on your test though, but as far as the AP test goes. All right. On 68, now we're going to use the squeeze theorem to evaluate this limit. So it tells me I want to find the limit as x approaches 0 of f of x. And it says that negative x squared is my low function. That's the function that's on the bottom of everything. And x squared is my high function. That's the function that's on top of everything. So if I can prove that the low function and the high function both have the same limit by squeeze theorem, I can say that that is going to be the limit for f of x. So I'm going to take the limit as x approaches 0 of negative x squared. And when you directly sub in 0, what are you going to get? 0. And then I'm going to do the same thing for the high function. So the limit as x approaches 0 of x squared. And when you directly sub in 0, you get 0. So because the low function, the one on the bottom's limit is 0, and the high function, the one on the top's limit is 0, what can I say about the limit as x approaches 0 of f of x? It's 0. So I'm going to say the limit as x approaches 0 of f of x is going to be also 0, and I know that by squeeze theorem. Yes, it's kind of like proving limits, but it's a little different.
If it's not the same, is it just unique?
No, so that's the next one will not be the same. So I'll show you what we'll write for the next one.
Do we have to put by squeeze theorem?
It's a good habit to get into.
Will it be like an FRQ or something that like ask you how you got it?
Yeah, yeah.
So is it going to be like an inequality?
No, it's not as hard as all that. All right, so on the next one, I've got g of x, which is my low function. And I've got h of x, which is my high function. And on this one here, the limit is approaching 2. So make sure you pay attention to the x value you're approaching. It's not always 0. A lot of times it is, though. Okay, so I'm going to plug into the g of x first, the low function. So the limit as x approaches 2 of negative x squared plus 2x minus 3. So I've got negative 2 squared plus 2 times 2 minus 3, which is going to give me negative 3. All right, so the low function limit is at negative 3. Now I got to do the same thing for the high function. So the limit as x approaches 2, and my high function is just 2x plus 1. That's the h of x function. Does that make sense? So 2 times 2 plus 1, which is going to give you 5. So the low function's at negative 3, the high function's at 5. Do we know where the middle function's going to be? No. And so what you're going to write, because you don't know, is you're going to write cannot be determined. And a lot of times that question, I've seen it on a multiple choice. I've never seen one where you have to write cannot be determined on a free response. But it was a multiple choice question in years past, and one of the multiple choice questions was like, there's cannot be determined, there's not enough information given, or something like that. If cannot be determined, I'm not sure. You could put not enough info. That would be like, I guess, a short way you could write that. Yep. Okay, and then the last one has a trig function, but it's fine. G is my low function. H is my high function. On this one, we are approaching 0 again. So the limit as x approaches 0, g is cosine pi over 2x plus 2. I made the mistake, but I'll fix it here in a second. I forgot my plus 2 in the first video there, so plus 2. Wait for it, it comes back. So when you directly sub in, cosine of 0 is going to be 1. And then, there I go. Plus 2 it's going to be 3. All right, so the limit is x approaches 0 of cosine of pi over 2x plus 2 is going to be 3. So my low limit is 3. And then I'm going to plug it into the upper limit. So the limit is x approaches 0, and the top function is x squared plus 3. So when I plug 0 in, I get 3. So because the low one is 3 and the high one is 3, what can I say about the limit?
There is enough information.
Wait, yes there is. What is it? 3. Oh, there is enough. Gotcha. Yep. Yeah, the plus 2. All right, so they both got to be the same thing for squeeze theorem to work. If they're different, you would say cannot be determined. That's different than limits. So if you're doing the left-hand limit and the right-hand limit, and the left-hand limit and the right-hand limit aren't the same thing, that does not exist. And if they are the same thing, then the limit is that number. Squeeze theorem is a little different. So was that kind of okay? Are we okay?